In this video, we will solve a basic degree of freedom problem. And so if you want, you can pause the video here and attempt the problem. And just as a recap, this was for degree of freedom. You can pause the video here and review. And so now we can solve this problem. So first, we will use degree of freedom to know if we can even solve this problem. So we can write DOF, degree of freedom. We first need to ask, how many unknowns do we have? 1, 2, 3, 4, 5. So we have 5 unknowns, N1 through N5. So that's 5. How many balances or equations can we write? So we can write a water balance, we can write an oxygen balance, and we can write a nitrogen balance. So we can write 3 balances. So just a recap, H2O, oxygen, and nitrogen. And we could, however, replace one of these things and instead say a total balance. Because if you combined all 3 of these things, it is a total balance. But you can't just say 4 balances, H2O, oxygen, nitrogen, and total, because when you have all 3, that is total. So what we could do here is say replace water with total, or replace oxygen with total, or nitrogen with total. But you can't add and say 4. So we have 3, total balances. So we say minus 3. So we still have 2 more things in order to make this problem even solvable. So now we need to think, is there any relationships? So if you notice, we have 100 liters of water. We know density of water, so we could easily convert this into moles. So that's one thing that we could do. So we can say density. Density of water is a relationship that we can do to solve this problem. So now we're still short one more. And here it says 90% of water in the feed. This is a relationship. So that's our second thing. And we say 2. So 5 minus 3 minus 2. And that's 0. And there's no more balances and or relationship. So this problem is solvable. And now we can first solve for N2 using this relationship right here. So we can say that N2 is equal to 100 liters of H2O per hour. It says hour. And we know the density of water can be written as 1,000 grams of H2O per liter. That's one way to write density for water. That's just density. So that's density right here. So we cancel this. We have grams over hour, but we want moles per hour. Moles per hour. That's what we want. So we can say that 18 grams molecular weight is 1 mole of H2O. And this would give us 5,555.6 moles of H2O per hour. And this is N2. So we just got N2. N2 is just solved. So we have 4 more things that we need to solve, but we use density. Next, we could use this 90%, this relationship here. We could say that N1 times 0.2, which is water, times this relationship, 90% of water in feed. So we would multiply this by 0.9, and this would ultimately equal N2. We know that N2 is this number, so we could say 5,555.6. And by doing this, we would get that N1 is equal to 30,864 moles per hour. So this is N1. So now we know N1 and N2, and we need to solve for these 3. So this is where the balances come into play. H2O, oxygen, nitrogen, 3 balances, 3 unknowns, and so now our problem can be solved. So I'm going to scroll down a bit. So if you want, you can pause the video here, write down what we have. And so let's solve for oxygen, nitrogen, and water to ultimately solve our problem. So oxygen balance. So the O2 balance, in our input, we had 30,864. We had 0.8 and 0.21. And that's going to equal to N3. I'm going to scroll up just for a recap. So 30,000 something times, we had 0.8 moles of dry air, while this part was 0.21. That's why we multiplied this times this times this. So that's going to give us N3, and if you want, you can calculate it. You would get N3 is equal to 5,185.2 moles per hour of oxygen. So this is N2 and N3. So now we have 2 more things that we need to solve for. So we need to solve for N2 balance, which would give us N4. So N2, which is nitrogen. We do the same thing as this. So 30,864 times 0.8 times 0.79, the composition of nitrogen. And that's going to equal to N4. So N4 would equal 19,506 moles of N2 per hour. So this is N4. Finally, we have an option. Do an H2O balance or do a total balance. Just to be kind of consistent, I will do an H2O balance. So we have the 30,864 times the 0.2. This was 0.8 for dry air and 0.2 was for water. And that's going to equal N5, which is what we want to solve for, plus 5,000, 555.6, which was our N2 stream. And by doing this, we would get N5 is equal to 617.2 moles of H2O per hour. And if you want, you can even check. If I go ahead and we scroll up, we can go ahead and check. If we add N3, N4, N5, and N2, that would give us N1. And that's why this is very important. That's why we could have replaced one of these with a total mole balance. But we can't just say this plus total mole. That wouldn't work. And that's all we need to do for this problem.